In item 3, we are looking at taxi cabs and their arrival times and trying to find out how long we're going to have to wait on average and the likelihood of those wait times, etc., etc. The big key here is to differentiate between what the time scale is versus what we're counting. Right? Counting X is our number of cabs. Our T is our time between cabs, or a wait time. These are very strongly linked, of course, but they are not the same things. One is technically a Poisson variable. The other is related to it, but it's a slightly different kind of thing, depending on how we're all going to approach this. Right? So that's why you see this kind of funky thing going on here. And Poisson random variable, here's the mass distribution function. That's for a discrete thing. That's the counting approach. Right? But it's phrased in terms of time by the parameter. Notice the expected value and the variance are the same thing. It's equal to the parameter of this function. Right? And that's equal to another one, lambda times t, where that gets us to the right time interval. Nu is this mean number of arrivals, and time t lambda equals the mean rate of arrivals. And that's what we've got to play with here as we ask, what's the probability that the wait time for the cab is more than 10 minutes using the Poisson model? What that's really saying to us is that, okay, the probability of t be greater than 10 minutes, the time scale is important, that is the same thing as the probability that x is equal to 0. No cabs given whatever the right nu value is. Right? Well, that's partially the key here. You got to go find out the right nu value. That's going to be equal to this lambda times t. Right? So our lambda that we have is 5 cabs per hour. The time frame that we have is 10 minutes that we're looking at. So we got to get this converted here. And so that's just 60 minutes per hour. And so our nu parameter is 5.6 or 0.8333 repeating. And so that's the key thing, and then it just becomes doing the math of, okay, the probability that x equal to 0, that's associated with then nu to the x and e to the minus nu over x factorial, where we're only looking at x equaling 0. So there's your nu to the 0, e to the minus 5.6. I didn't substitute in for the nu, over 0 factorial, because that's going to be 1, that's going to be 1, and I'm going to just be left with e to the minus 5.6. And that evaluates then to being 0.4346, or 43% or so for part A. In the second one, we're asked for the mean number of cabs per hour so that the probability that the wait time is more than 10 minutes is 10%. Same question that we just answered actually in part A. We are just changing it around a little bit. That we're going to set the probability of x equal to 0 for given nu equal to 0.1. We're trying to actually find nu such that that's the case. Right? And so when we do that, well, it's really going to come right back to the same thing here. That e to the minus nu now is set equal to 0.1 because of valuation that we just did in part A. And that then means that nu is equal to 2.3 cabs per 10 minutes. Asked to express this, though, in terms of cabs per hour. So we're going to look at 60 minutes per hour, and that gives us then the answer of 13.8 cabs per hour. Okay. And then in part C, we're asked to repeat part A using the exponential model, the probability that t is greater than 10 minutes. Okay, well now, if t is drawn from the exponential model, then here's that one. right, that the distribution is lambda e to the minus lambda x, you've got that the expected value of x is equal to 1 over lambda, that parameter that is there. Then we got to decide, is that the same lambda as we had before? Right, so that's, you know, some things you gotta look at. Right, so the mean wait time here is, well, it's 1 over what we had before. We had 1 cab per 5 hours. So the mean wait time is 0.2. Sorry, I got that exactly opposite of the units. I've got 1 hour per 5 cabs, so that's 0.2 hours per cab, or 12 minutes per cab, right? But the mean of t for the exponential distribution is 1 over lambda. Right? And, okay, so if we set that equal to 12 minutes, then, it really turns out that lambda is equal to 5 cabs per hour, right? Because this is 12 minutes per cab. Take the reciprocal of that, that's all, just take that right there, that would be the same thing. Or 1 cab per 12 minutes would be the same, equivalent, same thing, different units, but same thing, right? And that allows us then to start to evaluate what we want, which is now probability that t is greater than 10 minutes is equal to the integral from 10 to infinity of lambda e to the minus lambda t dt, or that's equal to 1 minus the integral from 0 to 10 of lambda e to the minus lambda t dt. Right? And when we evaluate that out, now you're going to get 1 minus, then this becomes minus e to the minus lambda t, evaluated from 0 to 10, and so we'll get 1 minus, or plus that is, e to the minus 10 minutes times lambda, and then that becomes minus a minus a minus, or minus e to the 0, which is 1. So the 1's drop out here, and we're left with e to the minus 10 lambda for the desired answer. And since lambda, this is 10, represents minutes now, so I want the lambda that's in terms of minutes. That's e to the minus 10 over 12, and that's the same thing as e to the minus 5/6. That's the same as before. 4.4346.